Good evening, everybody. I welcome all the students to Pune College of Arts, Science and Commerce, Camp Pune 1. I teach statistics, paper 2, discrete probability and discrete probability distribution. Myself, I am Dr. M.B. Pathan. In last lecture, we have discussed many problems which are related with elementary probability. We have solved the problems of 3 events with different type of information. All are having a common element, some are having common element and so on. Today, we'll proceed a new chapter under the heading of conditional probability and independence. We'll try to see today some definitions, and if time permit, we'll go for numerical problems. First definition is conditional probability. Definition says if capital A and capital B are two non-empty events of omega, then conditional probability of A given B is defined as probability bracket A. This vertical line you have to read as given. A given B equals, it is the ratio of two probabilities, probability A intersection B total divided by probability of B. You have reverse, another way of writing conditional probability. D given A is defined as probability of B given A equal probability A intersection B divided by probability of A. If you look these two definitions comparatively, you can see the numerator is common. The denominator depends on the given event. If B is a given event, we divide by probability of B. If A is a given event, we divide by probability of A. So there will be natural condition on this both definition. If I look this as a definition, probability of B should not be 0. That means B should not be 5. If I look this, probability of A should not be 0. That means A should not be empty set. A should not be null set. If I compare today's topic with previous chapter, in previous chapter we studied probability of event directly. In this chapter, we try to study probability by putting some condition on the main event A, and then we do the calculations. If I want to explain these two, I will take simple example. Suppose there is one organization, they want to select a candidate in their educational institute. The procedure will be advertised, given in the newspapers. Many applications will be received to the organization, and they will scrutinize them. And suppose they decided certain events. They write A as a male candidate. They write B as experienced candidate. So here, chance of selecting male, that will be PA. Chance of selecting female, that will be P of A dash. Chance of selecting experienced candidate, that is P of B. Chance of selecting inexperienced candidate, that is P of B dash. So these probabilities named as unconditional probabilities, which we have seen in previous chapter. Now, in today's topic, I am interested to select male candidate but having experience. So I am putting a condition on my selection, and that is called as a conditional probability. That means I want probability selecting male, but which male? Given that he has a experience. I may be interested to select female. So I write probability of A dash given B. That means experienced candidate should be there. Similarly, I can make a reverse. Chance of selecting experience, but from whom? Experience may be male, experience may be female. But I want to pick up experienced candidate from male. I can write probability of B given A dash. If my educational institute is for girls, I will give the preference for female candidate. So in such situation, we apply the concept of conditional probability. I think everybody get it. What is the meaning of conditional probability?
Yes, sir.
Now, this is not an original definition. It is derived from the logic. What logic? If event A and B are not related, that means A is not affecting B, then you have probability of A given B as a simply PA. So that is a different way of explaining conditional probability. Definition number 2, independence of two events. The two events A and B of omega are said to be independent if they satisfy following condition. This is a condition to be verified for independence of two events. Probability A intersection B equals PA multiply PB. This is condition to verify independence. From where you got it? You got this condition from these definitions. If I say B and A independent, that means A does not affect B. So under this knowledge, probability of B given A should be how much? It will be directly PB, because A does not affect B if they are independent. So under independence, your left-hand side, this is my left-hand side, this will be PB, and this denominator will be taken on left. So you get a condition under independence, probability of intersection should be PB multiply PA. But when? If they are independent. Similarly here, if A, B are independent, that means what? The occurrence of B does not affect A. So chance of getting A given B will be PA. This denominator will be taken on left side. So PA multiply PB is a probability of intersection. So under independence, conditional probability transfer in this form. So original condition of independence is P of A given B equal to PA. P of B given A equal to PB, because independence says occurrence of B not affect A, occurrence of A not affect B. And that is why whenever you want to see AB are independent or not, you have to verify this equation. To verify this equation, you need three calculations: chance of getting A, chance of getting B, and chance of getting together, simultaneous occurrence. If this equal to product of separate, you can claim A and B are independent. I generalize this for three events, pairwise independence of three events. Three events A, B, and C are said to be pairwise independent if they satisfy following three conditions. The answer coming from this word pairwise. I want to check independence of three by making a pair. So for three events, there will be three possible pairs: A with B, A with C, lastly B with C. So for every pair, I will apply this condition. Let us check. Condition 1, P of A intersection B equal PA multiply PB. P of B intersection C should be P of B multiply PC. P of A intersection C should be PA multiply PC. That means this is the original condition of independence for two events, and it is repeated for three events by three conditions. You have to check all these three conditions. If all of them are true, then you can say events are pairwise independent. Otherwise not. Now number 4, that is complete, may be called as mutual independence of three events. A, B, and C are said to be completely independent, mutually independent, if they satisfy following four conditions. Look the conditions 1, 2, 3. These three conditions repeated from your pairwise independent. In addition to these three conditions, I add number 4, where I took all three intersection together. If probability of A intersection B intersection C equals PA multiply PB multiply PC, if these four conditions satisfied, then I can say events are completely independent. Out of these four, if 3 satisfies and last does not satisfy, I will claim the answer A, B, C are pairwise independent but not complete independence. So I can say definition number 4 implies definition number 3, but converse is not true. If A, B, C are completely independent, they automatically pairwise independent. But I cannot claim if A, B, C are pairwise, They may be completely independent, they may not be completely independent. On the basis of these four definitions, we'll try to study some numerical examples. Example number one, very simple example, which is parallel to your previous topic. Suppose A and B are independent events of omega such that PA 0.5, PB 0.4. Then compute probability of union, probability of A dash common B, probability of A common B dash, probability of A dash common B dash. You can recall similar example I took in previous chapter. But in addition to this, there is one more information. That was probability A intersection B is given. Here, probability of A intersection B is not given. See how to proceed. Bit number one, probability of union, we have a theorem. Put the result of theorem PA plus PB minus P of A intersection B. In question, probability of B is given, probability of A is given, but this value is not given. How to develop? It is developed from this information. The nature of events are independent. And if they are independent, we have the definition. Under independence, probability of A intersection B equals PA multiply PB. 0.5 multiply 0.4 become 0.2. Now I got the value for this. So after getting this number, problem is exactly similar of previous chapter, what you did in your previous topic. Put it, so probability of union become 0.5 plus 0.4 minus 0.2. The result is 0.7. Let us proceed ahead. Second bit, probability of A dash intersection B. We don't have theorem for intersection. Take the help of Venn diagram. This is your Venn diagram. Entire square is a omega. Draw the two circles connected with visible intersection. Call one circle as A, other circle as B. This square is labeled as omega. Locate your event inside the Venn diagram. What the event says? A dash, A complement. How to write? In the description, outside of A, common with B. So I take outside part of A and which is common with B. This area I want. So easily how I can write it? I take entire circle of B minus this unshaded part, which is a common of A and B. So easily your Venn diagram says P of A dash intersection B equal PB minus P of A common B. Put values, get answer. Third part, probability of A intersection B dash exactly to this opposite part. So I have not drawn the Venn diagram. You can draw the Venn diagram here. And it is reverse part of this diagram is your answer. So result will be PA minus P of A common B. Put the numbers and simplify. The fourth part of the question is probability of A dash intersection B dash. You have De Morgan's rule, probability of A union B complete dash. So this probability is same as this probability. In previous chapter I told if there is a common dash, common complement, use a complement theorem. 1 minus probability of your event. You have this answer from bit 1, that is 0.7. So probability of A dash intersection B dash is 0.3. Example number 2. Suppose A and B are two events of omega. If P of A 0.8, P of B is X, any unknown number, probability of union is 0.9, find the value of X. If, so in this question, we want to decide unknown quantity X with some condition. First condition says, if A and B are independent, what will be the value of X? Second condition says, if A and B are mutually exclusive, what will be the value of X? So by using this information, we'll try to decide probability of B. Let us proceed ahead. We want to find X such that A and B are independent. Now, when the word is independent, you have a definition for that. Put the definition. Probability of A intersection B should be PA multiply PB. P of A given to be 0.8. P of B is unknown, given as X. So probability of A intersection B is 0.8 times X. Another information in the question is in the form of union. Use this information now. We have addition theorem of probability. Probability of A union B equal PA plus PB minus P of intersection. This is known to be 0.9, 0.8. This is unknown X minus this is 0.8x. We developed it. Solve this simple linear equation. 0.8 taken on the left side become 0.1. From this X is common, 1 minus 0.8, 0.2. In between there is a product. So this goes other side as a division. Multiply 10 numerator, multiply 10 denominator, 1 by 2. Result become 0.5. So under independence, value of PB should be 0.5. Now, if they are mutually exclusive, what will be the value of X? That we'll try to decide. We want to find X such that A and B are mutually exclusive. So we have probability of A intersection B 0. Why it is 0? Because according to chapter 1, sample space and event, A and B are mutually exclusive if they don't have common. That means A common B is phi, and probability of phi is 0. Use addition theorem of probability. Put the values which is given. This is 0. So x equal to 0.1. That means probability of B should be 0.1 under the condition of mutually exclusive.